Welcome to UniAssist's first video on electrical engineering. Today we're going to cover the topic of equivalent resistance. Now this is a very common exam question, but it is a very tricky topic, as you can get some pretty complicated circuits in your exams. So today we're going to go through some tips and strategies on how to approach these types of questions. So let's get into it. So the first thing I like to do when starting these types of questions is to work out where my parallel and series combinations are, and then simplify my circuit. So first step is to simplify. So by this, I mean we either calculate our parallel circuits or our series circuits. So let's quickly go through our circuit just to see if we can identify any possible simplifications to start off with. Starting on the right hand side, we've got 2 ohms connected directly to the 6 ohm, which is connected directly to the 4 ohm. So straight away, I know that these 3 resistors are in series. Another obvious one I can see are these 2 resistors. They're connected right adjacent to each other, so therefore they're also in series. So just with these 2 pieces of information, we can begin to simplify our circuit. So one thing that I really stress is that you shouldn't be afraid to redraw your circuit. So let me just add that here. So don't be afraid to redraw. You can redraw as much as you like, you'll never be penalized, and really it's just going to help you kind of understand the circuit a little bit better. So let's redraw now. So we'll keep the 2 ohm, and then keep the 8 ohm, so when you have resistors in series, you simply add them up. So these 2 will become 8 ohms, and these 3 will become 12 ohms. So now I'll sub that into my circuit. So I've got 8 ohms here, and I've got 12 ohms here. Okay, so after doing that, I should note that the question is actually asking me to find the resistance between points A and B. So effectively, I want RAB as my answer. So the next thing to do is to further inspect our circuit to see if we can make any more simplifications or recognize any subtleties in the circuit. So if I'm at point A and I want to find the resistance between point A and B, I can effectively ignore this 2 ohm resistor because it is not connected to anything related to point B. What I'll do next is I would kind of visualize a current that may flow between points A and B. So if I have a current coming into point A, like this, what would happen here is that I've got 2 branches to work with. That means the current can flow either this way or this way. And then once it reaches this point here, it just flows straight back down. So what I've noticed here is that I've actually got a short circuit in place. So this thing here, this connection here is a short circuit. So these are always going to be around in these types of questions to kind of trip you up. So that's another thing I'm going to add here is be wary of short circuits. So when you have a short circuit, it means you effectively ignore whatever is connected in parallel to that circuit. So this means that we can continue to simplify. So now I can simply redraw this circuit as these 2 resistors between points A and B. And as I said before, the current at point A splits off like that, which means straight away that I know it's going to be a parallel connection. So my final answer, RAB, is going to be 8 ohms in parallel with 8 ohms. And this is simply just 4 ohms. If you want to do the math, it's just equal to the inverse of 1 on 8 plus 1 on 8, which is equal to the inverse of 2 over 8, which is 4. That's the first question done. On to our second question. As before, we're going to follow these 3 basic rules to help us simplify our circuit. First thing I have to look for are parallel and series combinations. So here, it's not as obvious because we've got a fairly complicated circuit, but the first 2 resistors I notice are these 2 that I can work with. So they're definitely connected together in the same branch. That means I can simplify them to be a series connection, and they will sum up to be 60 ohms when you add them together. So now I'll redraw my circuit just to make things look a bit clearer. So here we're going to have the 60 ohms in parallel with another 60 ohms, this diagonal connection, and there's 7 ohms here. Okay, so as I was saying, we have a parallel connection here, so you can clearly see that these 2 share the same nodes here, so therefore these 2 are parallel, so therefore they become 30 ohms. So let's continue to redraw. So we'll go this way now. Okay, now just back to the question. We were meant to find the resistance between points C and D, so RCD. Now the next thing I want to do is be wary of short circuits. Now let's see if we can identify any in our current circuit. So you can see the current would flow potentially from through here, then it would split off here, and when you get to this point here, the current can either keep flowing this way or split off. But because current wants to follow the path of least resistance, it's not going to want to go through the 7 ohm resistor. So that means this resistor here is effectively void. So we have a short circuit here. Short circuit. So this will help us further simplify the circuit. So continue to redraw. Now we've got this 30 ohm connected by this diagonal to the 50 ohm and the 32 ohm. So what we have here now is a fairly straightforward parallel connection between the 3 resistors, because you can see that they're all sharing these same points, which I will label, so these are all common. So that means my final answer is going to be 32. So RCD is going to be 32 in parallel with 50 in parallel with 30 ohms. So mathematically this will be 1 on 32 plus 1 on 50 plus 1 on 30 inversed, and this will lead to a value of 11.82 ohms. So on to question 3. In this question, we aren't given any numerical values, but rather R subscripts. So this is not so uncommon, and it's something that you shouldn't be afraid of. Just because there aren't numbers doesn't mean the question is hard or difficult. We still apply the same principles. However, there is a little bit more work involved in that we have to maintain the exact R values and keep rewriting them. So I'll show you a technique that I use to avoid having to rewrite these resistances constantly. So as before, we're going to start with the same strategy. So we're going to look for any parallel or series combinations. So let's start here on the left hand side. You can see that R7 and R6 are both connected to these two nodes, which tells me straight away that these two are indeed parallel. So what I will do now is I will identify a new variable that I'm going to call, say, R subscript A, and that's going to be equal to R6 in parallel with R7. So simply put, when I redraw this circuit now, I will just replace that expression with RA. So now I've got this. Oops. Also take note that in this question we're calculating our resistance between points R, D, E. Okay, so now what we're going to do is see if we can simplify any further. So once again, returning to the left hand side, we can see now that we've got these two resistors RA and R5 are adjacent to each other, which means these two are in series. And now what I'm going to do is I'm going to define R subscript B to be equal to RA plus R5. So recall that this is actually equal to R6 in parallel with R7 plus R5. And now I'm going to continue to simplify. So this will look something like this now. So you can see that the circuit's simplified quite a bit compared to the very start. Okay, now we can continue to simplify this. So another thing that I notice here is that these two resistors here share the same node. And in fact, this also includes R3. So you can effectively see that these three resistors here are all in parallel. So now I'm going to redraw again with this new simplification, and that basically just gives me a very simple circuit. So I've got D, E, I've got R1, R2, and I've got this combination here which is RB in parallel with R4 in parallel with R3. Now the final step is fairly straightforward. We can see all three resistors are connected to get adjacent to each other. So we've got a series connection between these final values. So that means my final answer, RDE, is going to be R1 plus RB in parallel with R4 in parallel with R3 plus R2. Continuing to simplify this, I get R1 plus the value I calculated previously for RB, which was R6 in parallel with R7 plus R5, and all of that will be in parallel with R4, R3 plus R2. So having to algebraically simplify this is fairly complicated, so we'll leave it like this. But if you are given numerical values, you can simply just sub these into your calculator. Okay, on to our fourth and final question. Let's begin by applying our same strategies. So here in this question, it's a little bit difficult in that there's no obvious signs of any parallel or series combinations. So what we're going to do then is kind of move to our third step, is be wary of short circuits. So you can see that these 2 points here are actually shorted by this connection at the bottom. To kind of confirm this, we can imagine a current flowing from point F. So when it flows into this branch here, this node here, it will split off in both directions, and the current that's returning this way, once it reaches this point here, it can either branch out through the 4 ohm, or it can flow through this short circuit. So what effectively happens is that this 4 ohm resistor is voided. So that's the first thing I notice, and therefore I'm going to redraw my circuit straight away, just to see if that change is going to actually bring about further simplifications. So redrawing this, and because we got rid of the short circuit, I can connect these 2 points straight away. And for this question, we'll be calculating the resistance between points F and G. So RFG. So even after this initial simplification, you can see that the circuit isn't that simple. There's still a bit of work to do on it. And the changes that we're going to do aren't very obvious. So the first thing I want to do is recognize the idea of common nodes. So we can see here that this point here and this point here, they're effectively the same node because they're connected via this short circuit. So what that means is I can kind of translate this 5 ohm resistor to this same node over here. So if I could redraw that, it would look like this. So just to make things clearer, I'm going to redraw the whole circuit. And another thing to notice is that because this node is common here, and it's shared via this point here between the 6 ohm and the 3 ohm, that effectively means that these two are actually in parallel. And they have a common value, resultant value of 1 on 6 plus 1 on 3 inverse, which is equal to 3 plus 6 over 18, which is inverse, which is equal to 2 ohms. So I'm going to include that in my simplified circuit, so I can actually change this to 2 ohms. And as I was saying before, we were able to translate the 5 ohm resistor downwards. So redrawing all of this information together now is I effectively get something that looks like this, where this is my 5 ohm resistor and this is my 4 ohm resistor. So once again, we've gone from something quite complicated to a very simple circuit. The next thing I notice is that these two are very clearly in parallel. So they'll have a resultant value of 1 on 4 plus 1 on 5 inversed, which is equal to 9 on 20, 20 over 9 ohms. And then our final circuit is simply the addition of all three of these resistors, which are in series. So my final answer, RFG, is going to equal 5 plus 2 plus 20 over 9. And that gives me a final value of 9.22 ohms. And that's the end of the last question. So thank you very much for watching. I hope this was helpful and you've learned a thing or two. Don't forget to like our video, subscribe to our channel, and like our Facebook page. Thanks again. See you next time.